Hello everyone. Today I present to you the project I've been working on for the past 2 weeks. I made a model trebuchet that flings small objects using the power of physics. Here's a quick view of my initial goals and intended materials for creating this project. I didn't meet everything, and some things were adjusted, but I feel that overall I've been pretty successful. I mean, at least it does throw things. First off, let me explain how I built this and what I kept in mind during the process. So, the way a trebuchet works is that it utilizes a supported lever with a counterweight on one end and a projectile and a sling on the other. The purpose is to launch the projectile using torque, as these are very old machines originally used to lay siege on castles. So, one end holds a proportionally very heavy weight that is initially held in place, and once this is released, the torque should be very unbalanced by the clockwise force on the weighted end versus a small counterclockwise force as a result of the weight of our projectile and the unbalanced lever. This accelerates the entire mass clockwise as the projectile and sling gain momentum. After a certain point, we can see that the counterweight reaches an angle of 0 degrees with the lever arm. Once this happens, the system decelerates as the angle forces a negative torque to be done on the lever, assuming the way we were going was positive. It is at this point that the sling loses contact with the lever and the projectile loses contact with the sling. Our centripetal force has been removed from the object while in its own circular motion with the sling, and its tangential velocity carries it from there. And we know this by Newton's first law of motion, combined with principles of centripetal motion. Since the centripetal force is causing this constant change in direction, or removal of it causes the object to move in the direction that it was going in that instant. An object in motion stays in that same motion unless acted upon by an outside force. From here, our situation is simply projectile motion. Its distance and time of travel are dependent on the launch angle and velocity. If we had these values, it wouldn't be difficult at all to calculate pretty much anything about the projectile's movement, but unfortunately the trebuchet system has too many inconsistencies to legitimately calculate such a value that's 100% experimentally accurate. For example, the wood axle rubbing against the lever generates a surprising amount of friction that would not be negligible. We could calculate what its coefficient is, but this obstacle is paired with another. As the counterweight and string move, they perform different amounts of torque in each instant since their angles of forces are constantly changing due to the combination of gravity and rotational motion. So, I decided to use a different method of experimentation than I previously decided on since wind resistance is also going to get in the way. So, as far as the design process goes, I started by drawing out a prototype blueprint. I decided to go with wood for a frame since it's cheap and has both structural integrity along with good flexile and tensile strength to account for the violent movements of the trebuchet. Knitting string was also a low-cost decision, and it has held up very well on my design. My first basket design was clearly not the one that I'm using today. The primary issue that I was having was that having so many strings surrounding it made it pretty much any projectile get caught in them, stunting the launch. First, I decided to fix this by removing 2 strings, leaving it with only 2 left. While this helped, I still had nothing launching right. I realized that due to an error made in manufacturing the wooden pole, it had a large bump on it that caused the lever to stop at a certain point, essentially. Once this happened, a stronger centripetal force was transferred to the sling as its radius drastically decreased. I also realized that I needed to release the projectile somehow. This combination kept the projectile in circular motion without ever launching. I fixed this by allowing the sling to fly off of the lever. It's tied at the end as it rests on a bent paperclip to hold it until it reaches a certain angle. Once there, the normal force of the lever is unable to affect the sling projectile system. This design has been successful thus far, and it allows the projectile to fling from the trebuchet relatively uninterrupted. As an experiment, I decided to test how launch distance and time were affected by the weight of the projectile. Essentially, I wanted to see how different objects would fly off of the trebuchet by measuring how far they went from the initial launch X position, as well as their time of flight. So we know that X equals v initial times time plus 1/2 acceleration times time squared. I'm able to calculate v initial using the experimentally gained values of time and x displacement, and in theory there should be no acceleration in the x direction and a constant acceleration of 9.8 meters per second squared in the y. Of course that only applies to physics land, but let's see what our values for v initial look like without taking wind resistance into account. To start off, let's take a look at the 3 projectiles I used. The lightest was a Lego Yoda minifigure that weighed about 0.02 pounds. Additionally, I launched a small medal that weighed around 0.2 pounds and a pocket watch that weighed around 0.3 pounds. Here's a quick overview of the data. My average airtime for the Lego was 0.7 seconds with an average distance of 70.5 inches or 2.02 meters. The average airtime for the medal was around 0.5 seconds with an average distance of about 25.03 inches or 0.34 meters. Now you may be wondering why the values for the pocket watch are all 0. That's because it didn't really go to plan. So the object was too heavy for the system. It simply did not acquire enough acceleration on the way up to enter the sling's required circular motion or go anywhere except straight up or directly into my face. Next time I would definitely calculate a torque value using both ends of the lever to see if an object will work with the trebuchet. It definitely showed me some limitations of the abilities of my creation. But anyways, let's take a look at these v initial values. To find it, we take this equation and solve for v initial. At the same time, we must understand that the trebuchet does not launch from a height of y equals 0 with where it lands. So on a quick side note, let me explain how I got my values for T1 and T2. So T1 is the time between the start of the launch and when the object passes its y equals 0 point, and then T2 is the time between that point and when it hits the ground. So what I did is I put a video of a launch into Premiere. I checked it was about 0.7 seconds. It was using the Lego, and I was able to figure out how long it took for the object to do that first T1 motion, and basically I just applied that same principle and percentage to the rest of the numbers. Using these, we find this final equation for our vector total of x and y initial velocities. Here are the values I calculated. It's immediately obvious to see that there are some distinct differences between the data sets of the 3 objects. First off, let's look at our distances. Distance traveled appears to go up as the weights of the objects go down, and while mass is not directly related to the projectile motion equation we're looking at, it influences initial velocity. Thinking back to the way a trebuchet works, the average torque from the counterweight does not change between these experiment trials. What does change is the torque due to the sling as Fg gets larger with greater masses, causing a greater negative torque. Since omega is equal to alpha over time, this makes sense. V initial in the x direction will be a lot smaller than before, with heavier objects making them travel shorter distances according to the equation x equals v times t. Similar to distance, we can see a trend with time. As the weights of our objects increase, the overall time in the air actually decreases, and it has a similar explanation to our distance measurements. Think about it this way. Although mass really isn't a direct influence on many of our equations, like we don't see an m or an fg anywhere, we've established that higher masses lower our v initial. This lowers the v initial's x and y components. Distance is based on the initial x component, while time is dependent on our initial y component. And we know from the very principles of projectile motion that these two are separate. If we were to look at x velocity versus y velocity graphs of projectile motion in a frictionless environment, it would always look like this. Y velocity will always keep a downward slope of 9.8 meters per second squared, since gravity is the only thing acting on it. So greater initial y velocities make the object travel higher in the air. The higher it goes, the longer an object will stay in the air. Since velocity over acceleration equals time, this means that higher velocity means greater times in the air. In conclusion, I learned quite a few things from this project. The major themes that I use, like rotational, circular, and projectile motion, are certainly good things for me to have reviewed, and combining all of these concepts to culminate into a final product was really fun. Not only that, but I'd say it was helpful overall. Brought together a lot of topics that went together to create something that people used before anyone even had a decent understanding of these physical principles. It sort of joined the common sense and deep physics sides of it together. Like, for example, everyone knows that a heavier object on one side of a lever makes that side go down. At the same time, we'd explain that as a torque as a result of a force acting on an object with center axial at a radius away from it. Anybody can give a basic explanation as to how a trebuchet works without using physics principles, but building it can be and was a completely different story. I'd definitely say that my design isn't perfect, but I think it worked for the physics analyses that I was going for in my original goals. A few points that I'd hit if I were to do this project again would be to make a larger trebuchet, as well as making a better release system for the thing that I'm launching. Overall though, I think that although I probably could have made some more precise calculations with a better trebuchet and a controlled environment, I made a pretty cool final product that can at least launch LEGO Yoda into space.